So 10 questions, all chapter 5. Chapter 5 includes so no home circuits, no RC circuits. That will be on the next. That will be on the next exam, but not on this quiz. We're just going to strictly on chapter 5. So first thing is just magnets, basic properties of magnets, the idea of poles, north and south poles, opposite poles attract, like poles repel. No monopoles. You can't have a north or a south pole all by itself. The idea of domains, magnetic domains. Remember magnetic domains, if I have a material, a magnetic domain is like a little piece of that material where all the electrons spin in the same direction so that all their magnetic fields line up. So it's like an area of uniform magnetization within a material. That's called a magnetic domain. We all have magnetic domains, but in a permanent magnet, the magnetic domains are all in the same direction. So just sort of skim through your notes. You'll see questions like this in the old exams, and we'll see some in a second. I'll skim through some. Permanent magnets, know how they're made. In nature, permanent magnets. In nature, molten metal. In the Earth's magnetic field, it cools, and then that locks those magnetic domains into place as it cools. And then electromagnets, you run a current through a wire, and that generates a magnetic field. You need to know how to draw magnetic fields, or they go from north to south. So magnetic fields go from the North Pole to the South Pole. Understand the Earth too, that at the North Pole and the South Pole, this is the geographic North Pole and the geographic South Pole. That this is actually the southern magnetic pole and the northern magnetic pole. They're just opposite one another. So if I have a compass here, the North Pole of that compass points towards the southern magnetic pole, which is the northern geographic pole, and the South Pole of that compass points towards the northern magnetic pole, which is at the southern geographic pole. They just switched, that's all. The magnetosphere, that the Earth has this magnetic field, and then as charged particles rush towards the Earth, the magnetosphere protects it and makes that the solar wind go around the Earth, protects it. You're going to see 2 or 3 right-hand rule problems. Actually, I think 2 right-hand rule problems. Right-hand rule. We'll do some practice on this, but there are 3 applications. 1, 2, 3. The first one is the force on a charge moving through a magnetic field. The second one is basically identical. The force moving on a current-carrying wire. In these, I let my index finger go in the direction of V or in the direction of I for the second one. Let your middle finger go in the direction of B, and then your thumb gives the direction of F. This is V or I, either one. So we'll do some samples of those, but you'll definitely have a couple of those on your quiz. And then the third thing is if I have a wire, I let my thumb go in the direction of the current, and then my fingers wrap to give the magnetic field. And we'll see some problems where it combines both of those. We'll go through one of those. You probably have already done some of those on your own. I think we did one in class, in fact. So be ready for right-hand rule. I said only a couple of questions, but prepare you for the exam. Also be ready, too, that you can do it not only from a figure, but also from words. I'll show you some examples. If you work through the old exams, you'll see sometimes that I'll say, instead of giving you a figure, I'll say, the magnetic field is in the positive Z direction, or the velocity is in the positive Y direction. So make sure you can translate those words into the diagrams that we use. Then, let's see, magnetic force on a current-carrying conductor. There are 3 or 4 calculation questions, and those include using this, or maybe calculating the magnetic field here. Let's see, what is that? Mu naught I over 2 pi r. Those are on your equation sheet, right? And then the 4th equation that we have is if we have a coil of wire solenoid like we had today, the magnetic field at the center of that coil is equal to mu naught I over 2R, and then there's an N in front of this. Again, on your equation sheet, the way you tell the difference is the coil has the N in it. Okay? So just remember that, because a coil of wire is going to have multiple turns of wire. But a single wire is obviously a single wire, so you no need to put the N in that equation. So I think I'm pretty sure there are 4 calculations. But you know, unlike previous tests, these calculations, I think it's fair to say that they're simpler, that you're really just looking for the variables in the problem and knowing how to plug them in properly. But if you haven't practiced it, it's not going to be simple. You're just going to get there and you're not going to know what it's talking about. You know, motors and generators. A motor and a generator operate in much the same way. A motor, I have a current going through a wire. It sits inside of a magnetic field, and because that wire is in a magnetic field, it experiences a force. Let's see, let's do the right-hand side of this coil. I let my finger go in the direction of I. B is to the right, and so the force on this is into the page. My force on this side is into the page. The force on that side is out of the page. Y'all try it out. Current is up. Magnetic field is to the right. And so the force on the right-hand side is into the page. On the left-hand side, it's the opposite because the current is opposite direction. Of course, this is assuming that it's rotating on an axis. And remember we talked about that when it flips over, that I take this side, which is an up current, and put it over here. So before I had a down current, but then after it flips over, it's now going to have an up current on this side. So in order to make that work, you have to switch the direction of the current every half turn, and that's what the brushes come into play. I showed you that video about the brushes on the commutator. The brushes are just switches. If you've ever heard of anybody talk about changing out the brushes in a motor, that's what they're talking about. These are just switches that switch the direction of the current. The other alternative is to use alternating current, which automatically changes, or by the way that you create that electricity, it changes direction so many times a second, 60 times a second, in fact. That's why our electricity in the US is 60 hertz. That's the frequency. Okay, mass spec, you know how to do that. Mass spec, the idea is that if I have a particle traveling through a magnetic field, my velocity is here, my magnetic field is into the page, V is going to experience a force that's downward, and so it's going to travel in that direction. And the radius of this path can tell us what the mass to charge ratio is. So R is equal to, I always forget, what is it? MV over QB. MV over QB. And then from that, you can figure out what is the mass to charge ratio, because I know what R, I measure, that is. I give a particle V, and I give it the magnetic field that it travels through in this controlled environment, in this instrument that, I said, some of you may have used it. We have one in the department. If you haven't, you may in the future in whatever field you go into. So you can find the mass to charge ratio, and it's R times B over V. Finding that mass to charge ratio tells you what the particle is. We did a problem today where I gave you a table, and you had to calculate M over Q, and then you go through and you identify what is the unknown particle. I think today we did tritium. That's problem number 1 on the test. So make sure you can do that problem. I find that if you get the first problem right, it just boosts your confidence going into the rest of the problems. Problem number 1. Those are on most of the exams. Then the magnetic field of a long straight wire, I've already shown you that, and the magnetic field of a solenoid or a current loop. As I told you in class today, the magnetic force between 2 parallel conductors, we talked about that today, but that's not on the quiz. It'll probably be on the exam, but it's not on the quiz. Just to remind you, if I have 2 wires with the currents in the same direction, they experience a force that is attractive, because one of them generates a magnetic field, the other one then experiences a force because of that magnetic field. But not on the quiz, don't worry about it right now. But worry about it for the exam, because it'll definitely be on the exam. In fact, I'll probably make it a point to have it on the exam since it's not on the quiz. Okay, that's it. We'll go through the exam, but those are all the big topics. 3 or 4 calculations: force on a charge moving through a magnetic field, force on a wire, magnetic field due to a long straight wire, and or magnetic field due to a coil of wire. Hopefully those are gimmies, because it's really just picking out the numbers and plugging them in. There's not a whole lot of higher order thought on that. But like I said, if you haven't practiced it, it's going to be difficult. And then a couple of right-hand rules. That's 4, 5, 6, maybe 3 right-hand rules, I forget. And then a few things about magnet, maybe 1 or 2 questions about basic magnet stuff, mass spec stuff. Yeah, that's it. That's the exam. Okay? I mean, not the exam, that's the quiz. I really want 100% on this quiz. It sort of depresses me when I don't get 100%. Okay? Y'all can do 100%, right? Yeah. Many of you have. So let's... Questions. If you have particular questions, or I have all the exams we can look at. Yeah. 2016. Eight and 9. Oh yeah, so this is the problem I was talking about in class today, but we just sort of ran out of time to do that. I'm glad you asked. Number 8, I want to know what is the direction of the magnetic field inside the solenoid. Remember, I tried to draw that figure, but it was just hard to see. But this is a better figure because you can't see the backside of the coil. So here I have a current that comes in here, and then it travels around so that in these coils it's going up. So I can use my right-hand rule. Remember, thumb in the direction of the current, and then your fingers wrap around. I let my thumb go up here, and then it wraps around. Now, inside of the coil, which is here, let's imagine that my pen is this little section of wire right here. Inside of the coil, the magnetic field is going to be in that direction. Outside of the coil is going to be in that direction. See that? This represents this little piece of wire right here. So inside of the coil goes like that, and then outside of the coil it comes back to your right. But with a solenoid, I'm only concerned with the direction of the magnetic field inside the coil. And that's where all the stuff happens. So here, my magnetic field, was it to the left? Is that right? Yeah. So my magnetic field is going to be in that direction, to the left. All right, so that would be, for example, a right-hand rule problem. When I classify it, I classify that as a right-hand rule problem. Likewise, you said 9 as well? Number 9 is a right-hand rule problem. This one's a little more difficult because it's 2 steps and it's using 2 different types of right-hand rules. The first thing that you want to do is figure out what type of magnetic field causes this type of motion. So looking at my figure, I say, well, my velocity vector is in this direction, and my force vector is in that direction. You have to sort of work backwards through that first application of the right-hand rule. But remember, V, B, F. V is index, B is middle, F is thumb. Oh gosh, so sometimes you can take your sheet of paper and move it around so that it works better. Right here we can't do that. Looks like that, right? Am I doing that right? Yeah, it's hard, isn't it? Yeah, so V is down, F is to your right. So that means that B is in what direction? Into the page. That's right. So my magnetic field here that this particle is moving through is into the page. Okay, now I forget about that, and I say if I have a wire, and this is my wire right here, that's generating that magnetic field, what direction is the current? Well, I imagine my fingers are going to have to go into the page on the top side of that wire, which puts my thumb pointing to the left. Right. So my thumb is going to be pointing like this. So that means the current is to the left. Okay. Sometimes students just get confused, like they don't realize this represents the wire. So if you see a question like this, make sure you realize that's the wire. And then also there's two steps to this. That first I have to figure out the magnetic field, and then I have to figure out the current. Okay, Megan? Yeah, so to find the current, I know that my magnetic field is into the page on this side. So my hand can either go like this, or it can go like this, right? Because my thumb, the current can either go left or right. So it's not going to go up or down. So since I want my magnetic field into the page, I want my fingers pointing into the page on this side. And then they wrap around underneath the wire, and they come out of the page on the bottom side. So the full magnetic field on this wire would look like this. Okay? Does that answer your question? Awesome. All right, that was 8 and 9, is that what you said, or 9 and 10? Just those two. You have a question?
Yeah, so how did you know with your down and up was to the right?
So that's a good question too, and you'll probably encounter that. If I show you the path that the particle takes, so say for example, I have some particle, and I just say it goes like this, right? Initially, that particle is moving with a velocity in this direction. Now, the direction of that velocity changes over time. Like right here, it's going in that direction, and here it's going in that direction. The force that causes that change in the direction of the velocity is going to be a center-seeking force, a centripetal force. And so the force that causes that is going to be in this direction. So these are the two vectors that I'm concerned with. I have V in this direction. I have F in this direction. Well, I did it opposite of what I had before. But if I do that, I have V, F, that means my magnetic field has to be, oh, not that, sorry. My magnetic field is out of the page. Okay? It is important that you can look at a figure like that and see the path of the particle and figure out what is the direction of V or F or B or whatever. Okay? Other particular questions? Okay, let's sort of skim through. Be prepared for, basic magnetic field type things, like this is what role does it play in atmospheric phenomena? Aurora borealis. Logan? Okay, I was done with that. What's up? Yeah. So here, what is the direction of the force on the wire? Same as we did before. Direction of I is the same as V, right? So V and I, you can think of them as the same. Index finger in the direction of I, and then I have to rotate so that my middle finger is in the direction of V, and that means that my thumb is now pointing into the page. So my force on this particle is into the page. I mean, on this wire, I have a force. That's not really the right way to draw that, I'm sorry. My force on this wire, that's not the right way either. I'm sorry, it's Friday afternoon. My force is into the page. Okay, so that wire is going to be pushed into the page. Yeah, those are on most exams. So let's just look around here, but not on this one apparently. I'm excited to get to light next on Monday. We've been in electricity and magnetism for a long time. I say they're on most exams. They are on a lot of exams, so. But not on these. Oh, man. Okay, here's one. Okay, so here I have, this is, y'all notice which one this was? This is exam 3 from last spring, spring 20. So I have this loop of wire. It sits inside this magnetic field. The first thing that you have to do is draw the magnetic field. So a magnetic field runs from north to south pole. So that's the first thing you do, is draw the magnetic field. Then I just take a side of the wire. It doesn't matter which side I take. Let's just take this side of the wire. Here I have a current that is out of the page. That's my current. And my magnetic field is to the right. And then I want to know what is the force on that wire. Now, just a little tip to you. When you're doing a right-hand rule, remember all those 3 vectors are orthogonal. So here I have the z-axis taken up with I, and I have the x-axis taken up with b. So that means that the force has to either be up or down. It has to be either plus or minus y, because I already have the x and z axes occupied. So I is out of the page, pointing towards you. B is to the right. That means my force on that side is up. So my force on this side of the wire is up. I could do the same for the left-hand side, but I don't need to because the current is just switched. So I know that the force is switched too. So my force on this side is down. So imagine you're driving your car. If I pull up on this side, down on this side, that is a counterclockwise motion. So this thing is moving counterclockwise, at least for a half turn. It'll move counterclockwise for a half turn, and then it'll go all the way back. It'll flip-flop, okay? Unless you change the direction of the current every time. Or like in that video that we saw where they made the little motor, they turned off the current every half time. That was the marker. They used the marker to shade or to insulate the wire. That's to turn off the current every half turn. 14 is good. Let's look at this one. This is another good right-hand rule problem. Here, this is like the problem we did before, but just working in a different direction or in a different order. Here, the first thing you want to do is figure out the direction of the magnetic field. Thumb in the direction of I. It goes into the page on the bottom of the wire and out of the page on the top of the wire. So I have a magnetic field that looks like this. It's into the page right here. Although that doesn't really matter. But that's what the magnetic field looks like. And then I say, well, V is down, magnetic field is towards you. That means that the force is to the left. So my force is to the left, so this thing will move to the left. By the way, my particle's path will look like this. Right? It's a centripetal force, so it causes circular motion. It's a centripetal force, so it doesn't change the energy because the speed is not increasing or decreasing. Centripetal forces don't change the magnitude of the velocity, only the direction. The centripetal force is always perpendicular to the direction of motion. I think I said that. It's always center seeking. Everything about centripetal forces now applies to magnetic forces. And that's also the idea behind a mass spectrometer. Okay? As I said, you'll have a question like this one. You want to do this one right quick? Just make sure we're on top of it. All right, so I always forget, I always have to derive it. So QVB is mv squared over r. I'm sorry. You can just look on your equation sheet. V cancels, and I'm left with m over q. That's the mass to charge ratio is BR over V. I did that right? Yeah, that's right. So that's my mass to charge ratio is BR over V. Now you have an equation in your equation sheet that's the cyclotron equation, and it's like R is equal to mv over qb. Okay, but you want to solve that for m over q. So once I do that, that's B is 8, R is 0.5, over V, which is 4, All right, so that has a mass to charge ratio of 1. That's easy. This also has a mass to charge ratio of 1. Notice the others have mass to charge ratios of 2, 4, and 16. Just go through and find the one that has the right mass to charge ratio. These are just made up atoms or particles, so the answer is yttrium, which I think is a pretty good name for an atom. Yttrium and mamnium and cerium. I worked pretty hard to come up with those made up atoms. I'd like for somebody to adopt them. Okay? Coming out to do this one. We did this today in class. We did one similar where we had the 4 wires, and I wanted to know what was the net magnetic field. So let's do the one on the left first. The current is coming out. I'll do it in blue. That means that the magnetic field is in this direction, right? Right-hand rule, thumb in the direction of the current. It folds around in a counterclockwise direction. At point P, this magnetic field is in the same direction as A. And then for the second current is going to be a magnetic field in this direction, because my magnetic field is going to be circular like this. So the net magnetic field is going to be in that direction. So B is the right answer for that one. Okay. Again, when you come to light, it means you've gone too far. Now you'll see that word, and that means you've gone into chapter 6. It's a good exam. You'll probably have one like number 11. Remember I said there were 3 or 4 calculation problems. Nothing tricky about them. They're pretty straightforward. Most of these exams are pretty straightforward. In fact, other than the right-hand rule, if you're prepared, I don't think this chapter is really that difficult. Like the math is not that difficult. It's really, students get tripped up on the right-hand rule. That's why we spend so much time. You might think that's kind of silly, but I think that the right-hand rule is important because it helps you to think spatially about things. And often people aren't very good at that, to think in 3 dimensions. So that's why we spend so much time on it, because students struggle with it, and spatial thinking is just really important. So here, how far from a straight wire carrying 0.45 amps is the magnetic field strength? So if I have a wire, and I want to know what is the magnetic field at a certain point, is mu naught I over 2 pi r. Remember, on the equation sheet, I can tell it there's another equation that looks really similar, except it's missing the pi and it has an n. I know the n, that's going to key me in that I don't use that equation here because I don't have a turn of wire, I only have 1 wire, so there's no point in putting an n. This is going to be 4 pi times 10 to the minus 7. That's on your equation sheet, the permeability of free space. I is 0.45 amps over 2 pi times 0.04. I want you to recognize that your pi's cancel. This cancels 2. You have 2 up here. 0.9 divided by 0.04. I don't know, it's either A or C. I'm not sure what the answer is, but you can calculate that and find it. All right. As I said, not having RC circuits on this. So if you see anything about capacitors or RC, not on this quiz. On the exam, not on the quiz. Only chapter 5. So you look at these, you'll have 1 or 2 questions like this that are just, you know, conceptual things, facts about magnetic forces or fields. Let's just look at this. This is a magnetic force on a charged particle. Is the magnetic force parallel to the magnetic field? No. Orthogonal. Q, V, and B are always orthogonal to one another. It means they're perpendicular, not parallel. The magnetic force is always opposite the electric force. The answer to this is no. We'll address this. There's another question I want to look at. And then the magnetic force can change the energy of a particle. Can it change the energy of a particle? Can it change the magnitude of the velocity? No, it can only change the direction. Remember, kinetic energy, or energy of a moving particle, is 1/2 mv squared. Can't change this, so that's not true either. So E is the right answer for that one. None of those are true. Okay, so what I was talking about regarding electric fields. Let's go, I think, one of those past exams. We didn't do one like this in class. Like number 4. Here, it's really common to use magnetic and electric fields to direct a moving charge. We do that all the time. TVs, like old TVs, like the cathode ray tubes that we used to use. You haven't used them, but you know what I'm talking about, the big TVs and the big wooden cabinets. What they would do is they would use an electric field to move, to accelerate an electron, and then they would use both magnetic and electric fields that were crossed to direct that electron to somewhere on the screen. And depending where it went on the screen, it would make a certain color in that part of the screen. It's kind of cool, actually. Inkjet printers use this as well. They'll use crossed electric and magnetic fields to move a little drop of ink that's charged to a certain place on the page. We use this a lot in detectors too, because if you need to move a charged particle around, you'll use crossed electric and magnetic fields. Anyway, I want you to remember that F is equal to Q times E, and that the force on a positive particle is the same direction as the direction of the electric field. I say that if I have an electric field in this direction, that's E. If I have a positive charge, it feels a force in that direction. That's from chapter 1 or 2 or whatever. Here I want to know, what is the velocity of the electron into the, for what velocity of the electron into the paper will the electric force exactly cancel the magnetic force? So a couple of things here is I want to say that QE has to be equal to QVB. Okay? Because that's what it's saying. It's saying I want the electric force, which is this thing right here, to exactly cancel the magnetic force. That way, when a charge moves through this crossed magnetic and electric field, it'll just not feel any force at all. It'll just move straight through. And so I'm looking for V. I just solved this for V. My Q cancels. V then is equal to E divided by B. E is 2,000 divided by B is 0.8. 2,500, I think is the answer. Yeah, 2,500. Okay? This equation is on your equation sheet, but it's like chapter, I think it's chapter 1 or chapter 2. All right, what else do I want to look at? I'll sort of scroll through this. Here's some stuff about calculating the force on an electron as it moves through a magnetic field. Here's basically the same question. Stuff about magnets here. We did all these, I think. Here is a magnetic field due to a coil of wire. Have we done that? We might have. That's the magnetic field is equal to, that's always N. Sorry, I'm not good at remembering these equations either. Mu naught I over 2 pi. N mu naught I over 2R. That's on your equation sheet. Calculating that. Here I would have, here it's a ring, but N is equal to 1. Times 4 pi times 10 to the minus 7. Sorry, let me go back to that. N is often, for a solenoid or a coil of wire, more than 1. But here, it just says that I have a thin wire that's bent into the shape of a ring. And so then I have only 1 wire. Be careful of that, okay? You guys follow? Okay, here it is the one that takes N, but here N is equal to 1. Anytime I have a coil of wire, that's the one with the N in the equation. Times I, which is 2, divided by 2 times R. Here is the radius Often I'll give it in centimeters, but you have to convert it to meters. Just watch your units. You never go wrong with SI units. That cancels. It's like 40 pi times 10 to the minus 7. What's 40 pi? I guess it's 13. 13 microtesla. I'm pretty sure that's the answer. Okay. What creates a magnetic field? At its fundamental level, what creates a magnetic field? Moving charges, okay? The magnetic field cannot change the energy. It can exert a force. It can change the direction. It can change the momentum. That's an interesting point, that the momentum is a vector or a scalar quantity. Y'all remember? It's a vector quantity. This is a vector quantity, so that if I change the direction of my momentum vector, if you remember from last semester, this question isn't on the quiz, but you could see one like it on the exam. The momentum was equal to m times v. It is a vector quantity. It's different in that way from kinetic energy, so that if I change the direction of a particle's motion, it changes also its momentum. But if I change the direction of a particle's motion, it does not change the energy. Energy is a scalar quantity. Momentum is a vector quantity. So we begin to see something sort of peeking through from last semester. And I would expect that for the exam. I've tried to not do that on the quiz, but certainly on the exam. We did one like this one, number 14. Number 11 is similar to what we did before, except I'm just looking for R. Just remember, B is equal to mu naught I over 2 pi R. And then I solved this for R. Here's B, excuse me, I. There's B. Mu naught is 4 pi times 10 to the minus 7. Y'all get those right, okay? They're just plugging in numbers. So make sure I'm doing some simple algebra. Y'all get those right for me? Yes. Can you all commit to that? Yes. Awesome. Good. I'll hold you to it. Tammy, you have a question? No. Okay. Oh, look. Let's look at this one. So students sometimes struggle with this number 16 because, as I said, you may need to apply words to figures. So just remember, if it's traveling in the negative x direction, that's negative x, and that's my velocity vector. And the magnetic field points in the plus y direction, so that's B, V, B. So that means that my force is into the page. My force then is in that direction. Into the page. Is that plus or minus Z? That's minus Z. Our coordinate system, our right-handed coordinate system, that's why we use the right-hand rule, because we use a right-handed coordinate system. This is plus X, this is plus Y, this is plus Z, and then negative Z is back in this direction. Okay? Up, right, and out of the page are positive. Down, left, and into the page are negative. And then we get to light, so we're past the quiz. Alrighty. I think I've probably actually done most of the quiz today. I don't remember what questions are on the quiz, so don't hold me to that. But I've certainly done a lot of the same questions as what we have on the quiz. It might be the easiest quiz that we've had, so it's a good opportunity for you to make everybody to make 100%. I would be giggling happy if everybody made 100%. Y'all don't want to see me giggling happy. It's not a good, it's a little bit embarrassing. Okay? Is that all? Make sure you see me before you go. Just make sure I got your name marked off.